The next talk is Sören, and he will tell us about decompiling for constant time analysis.
All right. So I'm going to talk about constant time analysis and how you can use or cannot use decompilers for that. So before we start, I'm going to make a short introduction into formal side channel security, where I talk about the setting where the attacker and the victim are running on the same machine, and the attacker wants to get some secret values from the victim. Of course, the operating system forbids just accessing the data directly in the memory. But because we are running on the same machine, we will have side channels via hardware microarchitectural features like caches or branch predictors. And when the victim executes, you will leak some values to that. And all the attacker has to do, even though it's not that easy, he has to observe the values that were leaked in order to see some secrets of what we have computed on as the victim. And in the formal settings, what we want to do is we want to model the victim, right? We give the attacker arbitrary power, and we just want to formally model how the victim executes and what he leaks. And for that, there's constant time leakage semantics, which is just standard operational semantics. So we do not model like microarchitectural features like caches explicitly in the state. Instead, what we do is we attach the semantics some leakage annotations that every transition will give out. These are the observations that capture the leakages that we would send to the microarchitecture state. And that depends on the leakage model that you're looking at. In case of constant time leakage, this will be dependent on the executed instruction at each step. Being a load or store, it will leak the memory address of the load or store to through the cache. Or for conditional branches, you will see the branch outcome in the microarchitecture. So the security property that will ensure that no such attack is possible is called constant time, which means a program is constant time when for any two initial states that look equal to the attacker, so they are only different on secrets. When we run both initial states, we will collect the leakages along our formal semantics, and then these leakages have to be equal as well, because that means that the leakages that we observed do not depend on secrets, because our initial states were only different on secrets. All right, so the scenery becomes like this. On the left, we will just use a constant time program. Well, this should be been the victim program. We just have to make sure this is constant time. And then the leakages that the victim will make are harmless because they do not depend on secrets. So basically everything we have to do is we have to make sure our program is constant time. And for that we can employ constant time analysis tools like BinSec, which we have just seen presented. Oh, yeah. All right, so the basic idea is we just take our crypto library, we send it to the analysis tool, and it tells us constant time or not constant time. Well, it might not be that simple. What we are really interested in are the binaries, right? We want to make sure that the binaries do not have constant time attacks. So we're asking ourselves this about the binary. What if your constant time analysis tool is a source level analysis tool? Well, you could come up with the idea to just decompile the program and test it then, right? But the question is then, did you fuck up? Is the binary still constant time, or did your decompilation program do something wrong? Let's look at an example. This is MLKM crypto primitive, and I'm not going to go into the details, but it's a binary. What is important is this part, where we have a bit test on a secret message, and then we do a conditional jump on the result, which means we will leak a secret bit of the message. Well, when we decompile it with, for example, reddec, we will end with a code like this, where the highlighted part is corresponds to the bit test. And what we see is we no longer have a branch like a control flow branching, right? We have a conditional move here, which means the hardware microarchitectural features that would capture this leak will not capture this. So we have removed our leak from our program just by decompiling. So the scenery becomes like this. We have our binary, we decompile it into a constant time program, which means our CT analysis has no other option but to correctly identify the program as constant time. And that means that our decompilation part was unsound. And we've tested several decompilers, and they all have soundness issues regarding to constant time, which is not a surprise when you are real, because decompilers do not really care necessarily about constant time. All right, you might say, scrap that. I'm just going to use the binary tool, right? I'm going to use this constant time analysis tool that it works directly on the binary. Now, when you look inside of the tool, usually all of them, no, usually, that doesn't work, okay. But usually they will transform the program before as well, right? They will bring that into an IR, into an intermediate representation on which they can operate better. And they will also do some optimizations in order to reduce like the analysis time that they have to do. And then they might analyze it, and indeed, they will also say constant time in some cases. And we've identified this in 2 different tools, CTVerif and BinSec, though I should note that what we used was not like a binary from a real cryptographic library, but we handcrafted some examples where we thought like, okay, maybe this goes wrong, and it actually did. But nonetheless, right, you wouldn't want to have that in your tool. So let's look at the general setting. The general setting is that we have some binary, we decompile it, or if we want to say even more general, we have some program, we transform it, and then we have a target program. And what we would like to have is a little bit more formal intuition on what is a sound way to do this. And we have identified 3 properties: reflection, preservation, and transparency. So reflection says, well, your input program, if that is not constant time, then your output program should also not be constant time, which is the same to say, okay, our transformation does not remove any vulnerability. Preservation is probably already a little bit known to some people here. It's just the opposite. It says if your input program is constant time and I transform it, then the result is constant time. When you think of a compiler and you have a source level program that is already secure, this is the property you would want. And then transparency just combines both and says if and only if, right? So we neither remove nor introduce vulnerabilities. And with that, we can go to this picture. And what we want to do is, at this point, we want to use transparent transformation, because then we will get a non-constant time program that we actually can analyze. And that part here is sound. All right, let's look at how we know the property that we want. How can we prove it? Like, I have a transformation, how do I prove it? And before we do this, let's look at the particular preservation and reflection individually. And we're going to start with preservation because this is a property that is already, as I said, known to the compiler community, right? And usually what we do in compiler security is we employ a simulation, right? We relate some run of the target program, and our simulation will give us a run of our source program. Now, in our case, our semantics has leakages. And for most transformation, it will be the case that these leakages will not be equal anymore. And I mean, think of a dead load elimination. The load previous to the transformation would have leaked some value. If we eliminate it and replace this by a no-op, for example, it will not leak anything anymore. So the leakages will not be equal. Now, for preservation, what you can do is you can employ a leakage transformer and make sure that whenever your simulation relates some source trace, you can actually explain the target leakages in terms of the source leakages. So you have a function that takes the source leakages and produces the target leakages. And that helps with preservation. So let's look at the constant timeness of our target program. We will look at the second trace with some leakages. We will simulate that as well. The leakages will be mapped by our transformer still. And because our source program is constant time, we have equal leakages along both traces. Now, because t is a transformer function, so a function, it will make sure that then also in the target program we will have equal leakages. And that means that the target program is constant time as well. So this is the idea of how one proved preservation. And like this is a result that we did not come up with. This was already a given, or previous work, I should say. How about reflection then? Now, if you think of it, the property, if you take the contraposition, is basically very similar. Now, if the target program is constant time, the source program should also be constant time. What we do is we just take the same approach. We look at the runs of the target program. We take the simulation and map them to runs in the source program or in the input program. But this time, we employ a reverse transformer. And the reverse transformer does not explain target leakages in terms of source leakages, but the other way around, right? You get some target leakages, and the transformer should explain the source leakages. And then what you get is when your target program is constant time, of course, your source program is constant time because it was a function. So what you get is a modified theorem, if you will, where now you need a reverse transformer instead. About transparency, well, we know how to prove reflection and preservation, so we could do just both of these. But we thought maybe we can do better. What we need is the following, right? We need a simulation, and we need a transformer and a reverse transformer. The transformer maps from source leakage to target leakage, and the reverse transformer maps from target leakage to source leakage. And the idea that we had is, well, on the left, we already have many of these transformers. For example, in Jasmine framework, these functions, precisely these functions, are already defined. And for the reverse transformer, this is the ones that we want. What if we can just flip them, right? Flip t around to get u. Then you don't have a lot of work. You just can flip t. And then you can use t inverse. Now there needs to be a condition, so this is possible, right? You cannot just flip any function. The function must be injective. And that's basically the idea that we have, right? Like, just make the function injective. Now, this is the core idea, and it works precisely like this. But depending on how your simulation looks, and if it is not log steps, you need a little more details there. I'm going to skip it because the talk should be a little short. So the resulting theorem that we get is, all right, you have your simulation, and now what you need is just the transformer that you already had, but you have to make sure that it is injective. And then you get transparency for free. And we employed this to quite a few transformations just to see that leakage transformers are actually injective in some cases. And we found quite a few cases. We think this is promising to do more. All right, so this is the theory part done, basically. And we thought, OK, now we have this nice idea on transparent transformation. Can we make something work in practice? And we decided not to go with a very formal approach and make it in a rock. Even that would be very cool, but it takes a lot of time, and we wanted to do something that we can evaluate. So what we decided is to take RedDec, the decompiler, and make it more transparent. I'm saying the transparent here, but it is more transparent because we do not have guarantees. So we started with handcrafted likely to fail snippets because we already tested the tools and found examples where they fail. And we took every pass of RedDec individually and let it run on the snippets. And then we analyzed the outcoming snippets on did this pass behave transparently on our snippets? If yes, we kept the pass, and if no, we removed the pass from RedDec. And then we called that thing CT RedDec, right? The passes that survived. We tested it on a benchmark of binaries, which we of course not use in order to train or in order to test the passes. And we got the decompiled binaries, and what we saw is that this was already sufficient to make it RedDec transparent on all the vulnerabilities that we found in that we had in our test set. To comparison, RedDec already removed 45 vulnerabilities from them. To wrap up, we've seen that decompilation for CT analysis is unsound generally. We have seen a formal property that we can employ for the transformations that we do prior to analysis that will guarantee sound results. We have seen a recap on how one would prove preservation. And we have seen that injectivity of the leakage transformers is sufficient to gain transparency. And then we have seen how we can use the idea of transparency to make a more transparent decompile-then-analyze approach. OK.
Thank you. So first question.
Can you give a bit more details about RedDec? Like, what kind of optimizations does it do?
Oh, quite a lot, actually. I mean, it's like 60 different optimizations. About 10 of them are analysis passes. These are do not change anything. They just analyze, so they are trivially working. because they don't do changes from the rest quite a lot. They borrow a lot of passes from LLVM framework. So there's LICM, there's sub-expression elimination, I think, is in there. They have dead code elimination. I mean, very standard transformations, I would say. It's
and what? I don't want to steal time.
Okay.
Thank you. Kind of open question. Do you think there is anything specific to the decompilers that could break constant time that we wouldn't already find in the compiler?
I mean, the difference is not necessarily that the passes are different. I mean, there's probably like one thing that you don't have in compilation is like the recovery of control flow. This is something that you have in decompilation, but we could prove that in our framework, we could prove that that part is transparent actually, unless your analysis messes up big time. So if you can recover control flow, the transformation will always be transparent. Apart from that, I don't think so. The passes are very similar, I would say.
Okay, thank you.
There was one at the back.
And one difference is that when you're thinking of compilers, you often think about preservation, right? And when you think of decompilers, it's reflection. But if you want perfect compilation in that sense that you have transparent transforms, then it's similar, yeah.
I'm just a little confused. So RedDec is just a decompiler. Did you invent your own leakage transformers for this?
Again, sorry?
Did you invent your own leakage transformers for each pass of RedDec, or was that already part of RedDec?
No. For the passes that I showed you back here, that's too far forward, backward. I'm sorry. All right. So for the passes here, we did show that you can flip the functions around, the transformers around. For RedDec, what we did is we did not formally prove the pass is correct, but we tested them on the set on likely to fail snippets. And then if it behaved intransparent on these, we just removed the pass.
Okay, so time for one last question before the next speaker sets up.
Hi, thank you for the talk. So I'm curious, how hard is to find these leakage transformers?
I mean, I would say it's more difficult to find the simulation for a compiler pass, right? If you have a formal definition of your compiler pass and you already have a formal definition on how it transforms a program, and you have defined your simulation, you will immediately know how the leakages will be transformed, because usually a compiler pass where you have a simulation doesn't the simulation usually has very thin slices of code that it is looking at and relating, and therefore you mostly know quite fast whether the function that you see is injective or not injective.
Okay, so maybe really last question while the next speaker is actually setting up and getting a mic and everything.
So you didn't have to tweak any of the pass in there. You just removed when it.
We just removed them, yes.
Okay. Because I could imagine instead of. And then you wouldn't even have to prove transparency. Maybe it's not very clear, but
I'm not sure whether I understand. But you can chat afterwards if you want.
Yeah.